All right. Well, I'm excited to be here with you today. Let me begin by saying thank you for this incredible opportunity. Truly, we stand on the shoulders of giants. And without all of the hard work of the good people of NVIDIA, none of what we do would be possible. My name is Joe Sullivan. I'm the CEO of Mapware. Mapware is building the world's fastest, highest quality photogrammetry engine by leveraging GPU accelerated processing throughout the entire compute pipeline. Our primary focus has been in the federal space, including work for customers like the US Air Force and NOAA. At Mapware, we envision a world where you can effortlessly generate a digital copy of the physical world around you. Let me show you an example. What you're looking at here is a 3D environment that is constructed entirely algorithmically. It hasn't been touched up or manually altered at all. Using a commercially available drone operating for about 20 minutes under 400-foot altitude, they captured 480 images. Those images were then uploaded into our software to create this digital surface model. Each pixel in this model corresponds to about 1 centimeter on the ground. This process of moving from photos to 3D models is called photogrammetry. This is in sharp contrast to the existing processes of manual construction. Now, it might be easy to think about building a 3D model by hand of a small house or even a field, but try to imagine building an entire scene of a city. How tedious might that be, right? Instead of spending days and weeks toiling to construct a 3D object, we can reconstruct any environment in a matter of hours. The input complexity doesn't impact our overall reconstruction time. By capturing each of these images in precise positions, we're able to build a high-fidelity, realistic model. We do this by taking a whole bunch of photos at exactly the right position with the right overlap in order to be able to construct the scene. Why do this? Why go through all the trouble of making GPU accelerated photogrammetry? Why not stick with manual processes for object reconstruction or existing CPU-based photogrammetry? Well, the first reason is speed. We're able to build a process that's 10x faster than our closest match and 100x faster than CPU-based rivals. Second reason is quality. That processing gain in speed means that we can use all that extra time and reinvest it into the overall quality of the model. We can do things like increasing point density or reprocessing under different conditions because we're operating in a cloud-first GPU accelerated environment. And the third reason is fidelity. Those increases in speed and quality lead to higher fidelity models, making it possible to generate objects with greater and greater levels of realism. For engineering or simulation use cases, this is extremely important. It allows us to map an environment in 3 dimensions with very high degrees of accuracy and precision. Finally, the fourth reason to do this is return on investment. Ultimately, all of those factors translate into cost savings and efficiency gains for our customers. So what is photogrammetry used for? Another way of asking the question is, who needs a map? As we look at the market overall, there are a few broad categories of demand. First, the market is 84% federal, typically very large stakeholders, and then 16% commercial. Any situation where you care about the speed of refreshing your map or the level of quality and fidelity, especially on a large scale, is a meaningful stakeholder. Our software is being used for things like large-scale environmental monitoring and protection of endangered species and habitats. It's also being used for large-scale construction projects and to provide project monitoring and simplify overall reporting. Being able to create a hyper-realistic, fully immersive environment also has tremendous implications for gaming and simulation and training. We love the idea of supporting augmented reality and things like video game asset reconstruction. Any area where we take the tedious monotony out of digital asset reconstruction and automate that, that's really exciting for us. And now I'd like to introduce my colleague, Dr. Robert Harris. Dr. Harris is a principal engineer at Mapware and leads our photogrammetry development efforts. He has published over 20 peer-reviewed articles with over 350 citations. Prior to joining Mapware, he implemented CUDA-based molecular modeling in his postdoctoral research with the University of Maryland School of Pharmacy. And now here's Dr. Harris.
Our photogrammetry pipeline is the set of procedures and software applications that we use to take a collection of two-dimensional images submitted to us by our users and use that information to generate a 3D representation of the environment. Now, these images typically come from drone flights, but they can come from other sources like aerial reconnaissance or really anything else. The photogrammetry procedure itself is very similar to what our brain does when it takes the inherently 2D representations that it obtains from each of our eyes and merges them to give us a 3D representation and idea of what we have in our environment. Now, one could think of many different ways to do this. You could try simply some sort of simple machine learning model or something like that, for example. But the procedure that we use is sort of standard in the field that a lot of people do. We break the entire calculation down into sort of a series of canonical pieces. In the first step, we are examining each image in the data set, and we are looking for interesting points. So anything we can use to try to identify a particular point in an image so that we can then find that point in other images. Now, this is sort of like the first step in assembling a jigsaw puzzle, right? You can separate out all of those pieces that, say, have pieces of trees on them or pieces of sky, and by separating them out, you get some idea of how each of the pieces are arranged against their, local neighbors. And that's essentially what we're trying to do here. Now, there are a lot of ways in the literature to try to extract these key points. And they're all pretty ad hoc. There's really no best way to do this. And usually what you do is you take either a corner or an edge detector, and then you do some sort of mathematical manipulation so that the key point will be identified regardless of scale and orientation. Now, the reason it's important to do that is because if we're taking multiple images of the same scene from different angles, the camera may be further or closer to the image in question when it's taking its different images, and therefore the scale of the key point could change significantly from image to image. Additionally, the key points need to be independent of the orientation of the image for similar reasons. As the camera moves around, the angle in which it sees each key point is going to change. And so the key points themselves have to be independent of that angle. Once we have identified an interesting key point, we associate with it a high-dimensional fingerprint that allows us to identify that key point in other images in the data set. In our case, those fingerprints are 128 dimensional, so quite high dimensional, and each of them essentially is a unique representation of that key point. This part of the algorithm scales pretty well because each of the images can be considered completely independently from each other. So they can each be given to different servers and no communication is necessary. Once we have all of those key points extracted from all of the images, we can do the homography step of the calculation. In this step, what we do is we consider each pair of images by itself. So we consider the images pair by pair. And what we are trying to do is we are trying to identify, first of all, which images overlap, and second of all, if they overlap, what is the best possible linear transformation that would relate the first image to the second image. So if I have a point in the first image, how can I transform it to get the corresponding point in the second image? Now, the first step in this procedure is to identify which key points in the two images are the same. So for each point in image 1, we do a nearest neighbor calculation to find the nearest point in image 2. Now, this nearest neighbor calculation is quite expensive and kind of tricky to do because for several reasons. One, the fingerprints are very high dimensional, so approximate nearest neighbor methods can be kind of tricky for this kind of data set. Two, a lot of the data sets that we deal with are very low contrast. So, for example, in a forest, right, pretty much all the trees look the same, more or less. And it's very difficult to identify one particular region from another. And because of that, locating individual identical points can be difficult, and there can be a lot of spurious matches because they're not particularly widely separated in this high-dimensional space. Then, once we've identified all of the corresponding key points in this image pair, we can then calculate what is the best linear transformation that best relates those two images. We calculate what are known as the homography, essential, and fundamental matrices that relate the two images to each other. Now, as I mentioned before, there are a lot of spurious matches when we're trying to match key points between images. Additionally, there's a lot of noise in the key points themselves. Although we designed the fingerprints to be independent of scale and orientation, it's kind of only an approximation. There is some scale and orientation dependence there. Additionally, when a drone is flying over an area and it takes different images of the same spot, but separated by time, you can have things like the lighting change or things can move around. And if that happens, then the fingerprints may not be identical between the two images, and you may get the wrong corresponding point when you try to match key points. For that reason, when we calculate this best possible linear transformation to relate the two images to each other, we have to use robust fitting algorithms to perform that calculation so that our results are not particularly sensitive to the presence of large quantities of noise or outliers. And this is actually a general sort of thing throughout the entire photogrammetry pipeline. We do a repeated number of fittings, and we generally have to make sure that every time we do a fitting, we do it robustly so that we can handle the large quantity of noise and the presence of outliers that is pretty much an inescapable part of doing this kind of calculation. Now, once we have all of the homography matrices calculated, we can take that information and do what we call structure from motion. In structure from motion, what we do is we construct a low resolution, sparse, 3D representation of the environment. This is the representation that best reproduces all of those homography calculations that we obtained in the previous step. This calculation also gives us information about things like what are the true parameters of the cameras, how are the cameras oriented in space, things like that. And here is where we get our first good idea of how good the quality of our model will be. This is where we can first evaluate whether or not the data is going to generate a high quality model at the end. And again, like in the previous step, this is a fitting procedure, and we have to make sure that we use robust methods to do that because of the large amount of noise inherent earlier in the procedure. Additionally, if any of the homography matrices were spurious, for example, we may have identified that two images overlapped that didn't really overlap, that would constitute an outlier that the algorithm has to ignore. So again, we need to make sure that our robust algorithm is not sensitive to the presence of outliers. And this procedure is generally called bundle adjustment in literature. Okay, so now once we have the sparse model in hand, we can combine that information with each of the images in the dataset to construct a depth map. So what is a depth map? A depth map is essentially a topographical map that shows the elevation of each point in each image. Those points, for each of those points, it gives a depth of the point from the camera. And that information is the first time we get a really high resolution, accurate model of the 3D stuff that's in that particular image. Then, once we have all of the depth maps in hand, we move on to the fusion step, where we combine all of those depth maps into a final high-resolution 3D model of the environment, which we store as a point cloud. This is the point in the calculation where we have, sort of our final three-dimensional model that contains all of the information embedded in the images. Additionally, this is the point in the calculation where we geo-register the model. Up to this point, the coordinates in the model are being treated just as internal coordinates to the calculation. They're just chosen for convenience. They don't really represent anything in the real world. Here, though, we want to orient the model so that each point is associated with a real latitude and longitude in space. So how do we do that? Well, there's a couple of sources of information that we can use. First of all, each of the images from a drone flight typically is accompanied by a GPS estimate of its latitude, longitude, and elevation. Additionally, a lot of our users will provide known survey points in the data set. So locations in the environment that have known elevation, longitude, and latitude that we can then identify in each of the images. And we take that information and combine it all together. And we do, again, a robust fitting to find the linear transformation that best reproduces those known coordinates in space. And that way we can locate the entire model in true three-dimensional space in the real world. Then, although we have a three-dimensional model of the environment, it's not really in a format that a lot of our users want. So we then take that point cloud and we generate prettier more structured representations of the environment. This includes a textured mesh, a very common way of visualizing the data, an orthophoto representation, and a digital elevation model of the environment. These are fairly common sorts of files that can be then input into various kinds of applications for analysis. And of course, all of these outputs can then be passed to machine learning algorithms to try to extract more information about an environment. So for example, if you're flying over a disaster zone, you can use those machine learning algorithms to identify damaged buildings or just put down power lines or trees, things like that. Now we've gone over the full pipeline. Here we have an architecture diagram of our pipeline and how all of the information flows. First, a user will provide some data to our web application. The web application will then pass that data to a controller, which will split the data up into pieces and pass those pieces on to the sort of clouds of subsidiary clients that are doing each of the steps that I mentioned above. Typically, those clients don't really care about where that information came from. They just take, a small segment of the job, do some processing, send the information back. The controller then integrates everything, and once the model and data have been created, it alerts the web app to tell the user that their data is now available. And this kind of architecture is very flexible. We can easily manage load balancing and scale up or down for different demands on the system. And we can handle large volumes of data, as well as large data sets with large numbers of images. And that's how it works. Basically, everything moves through the pipeline in the steps that I presented above. And at the end, we get this unified data out for users to use.
And now I'd like to pass the mic to Tej Gagadan. A rising star here at Mapware, Tej is working to integrate artificial intelligence throughout our mapping workflow.
Hi everyone, I'm Tej, and I'd like to talk to you about Mapware's product VAST. VAST stands for Vegetative Analysis Software Toolkit. At the heart of VAST are machine learning and deep learning models which are trained for specific use cases. To elaborate, in one of our recent projects, we built a model to identify the location and the quality of habitat for an endangered species using predefined parameters. These parameters could include the types of trees in the ecosystem, their height, their age, or crown spread. We use different data types such as LiDAR, RGB images, infrared images, and ground truth for training the model. These image types are fused together in different combinations to create inputs with several channels. This helps the model learn elevation level and surface level features. Parallel computing and processing is key to pre-process large-scale data before training our machine learning or deep learning models. Adding to our previous example, we split the data over the entire landscape, which ranges over 40 acres, into square tiles to process them in parallel for computational efficiency. CUDA is very useful while developing these solutions, experimenting with different deep learning architectures. That is, training neural networks can be accelerated using the parallel calculations on GPUs. We can test various neural network designs rapidly and rule out the ineffective ideas and spend more time optimizing and iterating over promising ones, which is also a product of CUDA. For instance, training a simple convolutional neural network on the CPU can be over 100 times slower than when we use one GPU with large batch sizes. We use the deep learning framework PyTorch to train our networks, which use the data types called tensors to hold numbers, vectors, matrices, or arrays in general. PyTorch is written in C++ and CUDA, both of which are essential for computer vision-based projects. We use OpenCV, which also leverages CUDA functionalities for image processing tasks like segmentation to isolate the objects from their background.
Once again, I'd like to say on behalf of the entire Mapware team, thank you for the opportunity to present today. It is a privilege to be a part of the NVIDIA Inception program, and we look forward to a long and successful partnership. Thank you.